Okay, welcome to today's session. In this session, we will further discuss the philosophical significance of artificial neural networks. And for this purpose, Arno will first give a short overview of the development from making a mind to modeling a brain. You certainly remember this quote by Robert Dreyfus. And Arno, you will tell us something about this development. And for this purpose, you can share your screen.
I just wanted to review or to have a look back to the seminar and the development of our approaches to AI research. There is AI research. It's a very technical field. It's a very old field already. It connects to biological research, it connects to philosophical questions, it connects to engineering questions in the field of what developed as computer science. And we started by a very specific question, a very philosophical question. And the perspective on this kind of research shifted, I think, in the last weeks in the text that we discussed. So we started by Turing and related Turing to Searle. And in this context, it was totally clear that for Searle, there's one decisive question, namely the question if a machine is intelligent. And in a way, the Turing text already disputed in advance, let's say, disputed the sense of the question to ask if a machine is intelligent as such, and tries to describe a different kind of setting for answering for another question, namely the question, in what case would we call a machine intelligent, regardless if it is as such intelligent or not. So here in this first, let's say, constellation around AI research and its theoretical reflections, the question what an intelligent machine is, or in what way we would call a machine intelligent, this question was crucial. And it was connected to very much the question of a rule-based operation with symbols, the Turing machine, and a very specific understanding of thinking. And this is the point of this kind of quote, from making a mind to modeling a brain. And this is very crucial for the question or for the observation of Dreyfus in the 80s. Something happened, something developed in the field of AI research itself. Namely, there's another paradigm already very old also, starting at the latest in the 50s and gaining momentum, let's say, in the 80s. And this new kind of paradigm, which is so crucial today, is linked to another kind of machine, let's say, to artificial neural networks, which are inspired by neurological research in the human brain. And this kind of research is very much connected to another kind of perspective, theoretical perspective, or perspective of interpreting this kind of machine, namely, it is much less answered if this machine is intelligent or if we would call it intelligent. In this context, it's much more the question, does it model the brain? Yeah? So it's a question of modeling. Yeah? So the starting point here, and that was crucial for Smolensky already last week, is a specific constellation of, let's say, ignorance. Yeah? We don't know exactly how the brain works. We know some things about the brain, and we get more and more knowledge about the brain, but we still don't understand it completely. We are far away of this. And we have machines which are inspired by these by brains, by our knowledge about brains, which do we understand the machines? That's an open question, but we can use them as a kind of model for the human brain. So we have, in a way, two sides of ignorance: the human brain, we only understand to some extent, and specific machines inspired by the human brain or by other kinds of brains, which we also don't understand exactly possibly right now, but they work rather good, today at least. And we can use them as model for the human brain. So in a way, we try to understand better the human brain and to understand better at the same time the machines that are inspired by them. But this is a question of modeling. And this was the question which was crucial for Smolensky, which is crucial for cognitive scientists, and what is also crucial for many people working in this field, thinking theoretically about AI research, about deep learning. Sometimes they are more cognitive scientists, sometimes they are much more philosophers. These are credible differences very often in this field. And one example for this kind of question about modeling a brain by the help of specific machines inspired by neurological research about the brain. For this kind of perspective, I find a very interesting representative, Cameron Buckner. He works in the US. I think he's a rather young researcher, and he published very different articles, which are very, let's say, very much in contact with AI research today, and which tried to connect it with questions of the cognitive sciences, how we can understand the brain and its performances, and with philosophy. So especially in a very interesting text, Empiricism Without Magic, he tries to establish the thesis that in a way, when we understand specific neural networks today, it helps us to understand better a problem which is very old and which is linked to empiricism in the 18th century. And then when we understand the machines and their performance, we can solve the philosophical problem in a way of the 18th century. So he really connects cognitive sciences, philosophy, and a deep involvement in the current state of research in the field of artificial neural networks. So, but the basic perspective is modeling the brain. And what is interesting in the case of Buckner and the text of today and the other texts of Buckner is that he doesn't stop with the general claim that you can easily make. For example, you just can say artificial neural networks are modeling the brain. But if you want really to exploit this kind of approach, you have to get specific. Yeah? You have to specify, okay, what kind of artificial neural network? There are a lot around. They are a lot developed in the engineering computer science. What kind of artificial neural network is a model for what kind of performance of the human brain? You know? And against this background, Cameron Buckner was very much interested in a specific type of artificial neural network, and that is called convolutional neural networks. This is a little bit in some fields of artificial intelligence or machine learning, or more specifically deep learning, which was a little bit booming in the last decade. This specific type of network, of artificial neural network, was possibly most prominent, most successful in the last 10 years, I would say. This is a depiction of an article of Krzyzewski and others from 2012, I think, and which became famous for this specific type of network, this specific kind of implementation for winning a kind of contest, a contest that was made for many years already, and it's about recognition of objects in a database of photographic pictures called ImageNet, and that's why this contest was also called ImageNet, and this kind of neural network won 2012. And since then, I think it more or less is dominating this kind of field. Today, there's a new trend called transformers, but for around 10 years, I would say convolutional neural networks in many contexts were totally dominating and very much attracting attention of many, many people. So that's why I would like to, and this kind of network is also in focus of the text of Buckner and other texts of Buckner. And I just would like to give you a small technical introduction into this kind of network. This kind of depiction is rather abstract, and it possibly doesn't give you any idea what's happening here. And I would like to give you at least a kind of intuitive understanding what happens in this kind of network. And first and foremost, it's necessary to distinguish two operations or two types of parts in this network. And the one is called convolution and the other is called pooling. No? And I try first to give you an idea about convolution. Convolution is linked to what we call filter or kernel. And this is a very simple thing. It is used in manipulation of pictures and in many, many other fields. It's just the following kind of computation. You have something like a picture here, which is directly translated into number. Here it's a grayscale form. And you can just go through this kind of pixel matrix and multiply it with a matrix that you arbitrarily define. No? So you have just numbers here. There are grayscale numbers for this picture, and then you can multiply it with different kinds of matrices. No? Just a moment. It doesn't work. Just a moment. The result is here. Excuse me for that. I was a little bit irritated. This is just the grayscale original picture and the original picture as a picture. And then you multiply squares, three with the edges. You multiply it with the kernel, which is just numbers. And then you get something like this. This is the original picture on the left. No? You have here the kernel, you make this kind of multiplication, and then you get a different kind of picture. Each multiplication with the kernel and 9 dots in the original picture gives a new dot, which is shown on the right side. This is very light. Here it's very dark. No? And you do this line for line, the whole picture. And then you get something like this here on the right side. And it seems to be immediately clear that this is just computation. It's just number crunching, but at the same time, it obviously seems to highlight specific aspect. Here's something like the horizontal edges. No? And this is called topsoil. No? You can multiply it with a different kernel, and then you get what right sobel are. So now it's highlighted what the right sobels are. Or you can blur. You can try to construct an outline. And it seems to be, or I find this very interesting and very fascinating because it's just a simple multiplication or a lot of multiplications to be serious, but nevertheless, the result has a specific meaning. It seems to extract specific features of the picture. No? And this kernel or this filter is a crucial part of a convolutional neural network because what you do here, for example, you have a picture with three different channels for the three basic colors, RGB. So you have a picture of 224 pixels to 224 pixels and three channels for the three colors. And then what you do is you apply one kernel, for example, for the right sobel, you apply another kernel for the left sobels, and you can do this with many kernels. Yeah? In this case, someone decided, or Krzyzewski and his group decided that they use 96 kernels, and every kernel presupposedly extracts a specific information, extracts specific features. And what you do afterwards is you reduce the size of the picture of the result. So here, obviously, the result was 55 to 55 here, and then you take something like the maximum of each 2 × 2 square. That is called max pooling, and then you have 27 to 27 in size. And what you do here in a convolutional network is you multiply with kernels, then you reduce the complexity by something like max pooling or average pooling, and then again you can use convolution or multiplication with kernel and filters. That you do one step after the other, and at the end you have something what is called a fully connected layer, and that finally ends up with the output and with an estimation of what can be identified in the picture. I give you an example which is very nicely visualized. This is a trained convolutional neural network for the recognition of handwritten numbers. And what you can do here, you can draw a number, and then you see here the input. These are the first 6 kernels. That's why you have 6 transformations of the first pictures. Then you have, I assume, a max pooling that is reducing the size of each of these pictures. And then you have further convolution, and you have further poolings. You have finally the fully connected layer, and in the output, you see here, you have the estimation that it's a 1. Yeah? And the second guess, which is the second probable output, would be a 9. Yeah? So you see here very nicely visualized what happens in such a convolutional network. It is convolutions or multiplications with filters and kernels, reduction of the size and complexity. This is pooling, again kernels, again pooling, I would say, and finally layers that reduce in a way what these convolutions extracted on a visual level from the input, reduce it to a specific output, to a probability for the possible outputs. In this case, it's only 10 digits. So you have to have 10 possible outputs at the end. That can be much more complicated if you want to recognize animals in pictures or something like that. But the basic idea is exactly this.
One question, Arno. One participant asked us, could you explain what a kernel is? How can we understand the function of a kernel?
Yep, I can do this because the kernel is just this matrix, which is fixed and which moves and which is multiplied with every small square 3 × 3 in this context. So you have these 9 pixels here. I hope you see this red square on the left picture. You have this red square, and you multiply it every pixel with you multiply this square of 9 pixels with the kernel, and then you get 1 pixel on the right side, this very black one here. Then you move the square and the 9 pixels in the original picture. You multiply again with the same kernel, you get a second pixel. Then you move again, 1 to the right, and possibly you can also move 2, or that depends on the specific configuration. Then you get a third pixel, and you can move on pixel for pixel, and you get again and again a result. And the kernel is just this fixed matrix, which is multiplied with every possible square here in the original picture. Okay? Now, that would be, yeah, this is number crunching. But for sure, it's decisive what the filters are, how you specify the filters. Yeah? Here in this case, I just define something. I can choose it arbitrarily here. So, but I have to know what I use in a way, yeah? What kind of effect I have with what kind of kernel. But in the case, whoop, I'm looking for my window. But in the case of a convolutional neural network, the point is you don't specify the filters from the beginning by hand. They are the result of learning. Yeah? This is decisive. So what you do when you train the network is you hope to specify the filters in such a way that they learn what is decisive for example, identifying cats in pictures. Yeah? So the kernel are the result of a training process. They are not given by the modeler or by the programmer or so. So the network should learn what features to look for in the picture in order to recognize something for which we train it. Yeah? And what is interesting then is if you train such a network, and if it works, so you can just check, is it really recognizing cats? And if it's recognizing cats, then it would be interesting to look or to examine what is it looking for? What are the kernels that were the result of a training? And that you can do. This is a paper of 2014, I think, from Zeiler et al. You can try to visualize what the kernels are looking for, what the convolution in a way is triggered by, what are the aspects in the pictures that are helpful to identify a cat. And then you get pictures like these, or more recent paper is this on Distill from Chris Ola and others. They tried a much more elaborate kind of visualization that tries to show what the convolution is trying to identify in the picture and what kinds of features are extracted and are contributing to the identification of objects in the pictures. And what is a kind of general observation when you do this is that at the beginning of a convolutional neural network, there are really basic features that are extracted. Something like sobels. Yeah? Horizontal sobels, vertical sobels. And then there's a kind of abstraction process. It's getting more complicated. It's starting to configure specific different kinds of sobels to specific kinds of forms. And then it's getting more and more abstract, and it becomes more and more object-like, let's say. And this kind of performance is, I think, crucial in the argumentation of Cameron Buckner. This kind of abstractive process that is performed here in this kind of computation. That is in the focus of Cameron Buckner's approach. That is what I wanted to introduce. You know, I'm not a computer scientist, but I hope at least it wasn't too incomprehensible. You got some idea how this works. Do you have any questions in respect to this introduction? Else we would proceed with the questions on the text.
I think we can have the discussion afterwards because I'm recording the session. So Arno, thank you very much. So now I will share my slides and proceed to the key questions for today's session. So first, we changed the key questions a little bit because we had another text also in mind concerning the questions that we sent to you. We had also the other text in mind. So we think that these three key questions that we are now presenting are a little bit more applicable to the text that we sent around. So the first question is, what are the main features of deep convolutional neural networks, DCNNs, and how do they relate to their technological predecessors? The second question is, what are the reasons for the success of DCNNs and what are their limits? And the third question is, how does AI supervised learning relate to the learning of human learnings? What speaks in favor of a close relationship, what against? So we see it has to do with empiricism in a way, and also with abstraction. So it's also a psychological learning, psychological task, and also philosophical, empirical philosophical task. So now we will form three groups and breakout sessions. So have a look at these questions. Again, I will have them at the slides. And now I will stop the recording and then we can discuss these questions.